Okay. So let me get to the concept of dynamical symmetry. Okay. Here I repeat a few things that I said previously. First of all, these are all Lie algebras. This is the symmetry algebra. This is probably the one which you are most familiar with. And so the most obvious symmetry algebra is the case that I discussed, that the symmetry algebra is SO3. So it is this Lx, Ly, and Lz. Okay? And with the notion of symmetry algebra, one means that for all G belonging to the symmetry algebra, we have the property that the transformations commute with the Hamiltonian, right? So if you have a rotationally invariant Hamiltonian, this Hamiltonian will commute with Lx, Ly, Lz. They form an algebra, so I wrote down the commutation relations for those operators. And so that means that the symmetry of the Hamiltonian is SO3. And the Hamiltonian can be labeled, the wave functions can be labeled by a quantum number L, and all the magnetic substates, so ML minus L to plus L, they are degenerate in energy. Yes?
So this statement here, H commutes with all the little g's, does that mean H is also a Casimir operator on the group?
It's not... no, I don't think so, because H might have other... Yes, because that would be very restrictive. So that cannot be the case, right? Because then there is only one choice. In this case, for instance, an H must be the Casimir operator of SO3. There is only one, which is L squared. And clearly you can have more. So it just says that well, I guess I should continue and try then to explain, but I don't think you can say that. Okay, so this is symmetry, dynamical, the symmetry algebra, the dynamical algebra, right? This is just an algebra with generators. So this is a set of generators Gi. So in the case that I discussed, this was U alpha beta. And the only requirement is that all the observables can be written in terms of those generators. Like the Hamiltonian, we could write the Hamiltonian in terms of the U alpha beta. So a concrete example was this U omega is the set of all the operators U alpha beta, and we could convince ourselves that the Hamiltonian can be written in terms of those generators. So this is the notion of symmetry algebra and dynamical algebra. It is certainly the case that in this case, so H is not necessarily commuting for all. Well, this is, I should maybe a bit misleading, but you see the point that in general, if you have an element of the dynamical algebra, it will not commute with the Hamiltonian. It does commute in the case of a symmetry algebra. Okay, so now suppose that you have a classification. So this is a very large group, right? If you want to know, for instance, the dimension of this group, the number of generators is omega squared, right? So this can be a very large number, whereas we saw an example, the symmetry algebra, we just have 3 generators. So the number of elements of SO3 is just 3. Okay, so this dynamical algebra is very much larger. It has very many more transitions than the symmetry algebra. Okay, so and in general, you can find algebras in between them, and this will be discussed in many of the examples. For instance, in the IBM or in the shell model, you can look at intermediate algebras. And now let's suppose, and so this is now the notion of dynamical symmetry, right? A Hamiltonian with a dynamical symmetry, right, will be written. So we have some coefficients, let's call them kappa. Then I can take arbitrary orders of Casimir operators, and I can take algebras which belong to this reduction. And here I have a summation over R and over M. So these are just coefficients. Okay. And these are Casimir operators. So this is a Casimir operator of order M. Right? So that means that if M is 1, it's a linear expression in terms of the generators of this algebra. If M is 2, it's quadratic. You also see that this has to do with the order of the interaction of the particles, right? If you have one body and two body, one body is single particle energies and two body interactions, then you should be able to write, I mean, you can take Casimir operators up to order 2, because this will correspond, this will give at most a two-body interaction. And then the last thing here, so this is the Lie algebra. Right? And an important thing of this Lie algebra, it should be belonging to this chain. So it should be 1 R or G2 or J symmetry or whatever algebra that is in between. Okay. And this looks like a little abstract, but especially in the lectures on the IBM, this will become much more concrete, right? And you will see that what is the usefulness of this kind of expansion.
R runs all over these groups.
Yes. So if you if you want to write it explicitly, I would say R goes from 1 to P. I've called here the symmetry algebra the last one, P. And M goes from, well, 0 is a constant, so that's not interesting. So, but in principle you have linear, and to a maximum, let's say the order of the interaction, I don't know, let's say 2, right? If you have M equals 1 and 2, linear and quadratic Casimir operators, you will have one body terms and two body interactions. That's okay.
But what's the extraction is like we have some system that have some symmetries. So we look at these symmetries of this group of this system. Then we construct this symmetry group, and then we go over this chain up to the dynamical.
It's rather the other way around. So as I did, I defined the dynamical group first because I want to know.
But how do you know that when you look at some system, it's much easier to determine the symmetry of the dynamical group, isn't it?
Well, the symmetry group, it's often it's also obvious. You know, for instance, rotational symmetry. This will imply SO3 isospin symmetry. This will imply this will be rotations in not unitary transformations in isospin space. This is SU2.
And then you say, I take all the Casimirs operating this chain.
Well,
No, this coefficient will be 0.
which ones?
This,
These can be arbitrary,
even 0.
even 0, if you wish, but that's not so interesting because then we have 0.
And then I have some big Hamiltonian and try to solve it.
Well, let me make one more point because I rewrite the Hamiltonian that I had. Well, maybe I should shift a little for people over there. Right, if you remember, I had this Hamiltonian in second quantization. Let's do it for and I can rewrite it in terms of my generators. Okay, these are coefficients, right? I mean, I don't care how they are exactly, but I can define it in terms of the generators. This is also a generator. So this would be U alpha alpha. Okay. So everything is written in terms of generators. These are related to two-body matrix elements. These are related to single particle energies. So now, these are expressions in terms of the generator, so in terms of the coefficients U alpha beta, right? So you will see that this is just a particular combination, a particular choice of single particle energies and two-body interactions here. Right? It's very important to understand that this is the general Hamiltonian. This is, if you write a Hamiltonian with a dynamical symmetry, it's only a particular, this is a subset of all possible Hamiltonians over there, a subset. Right? So I'm not claiming that you can do all Hamiltonians, solve Hamiltonians, all Hamiltonians with, that they all have a dynamical symmetry. This certainly is not the case. It's only for particular choices, epsilon and v, that you fall back to this kind of form. Okay. Now, what is the advantage of writing it like that? This can be expressed in one equation, actually. Namely, if you look at this property, the Casimir operator of any algebra of any order belonging to that chain, right? You take the commutator of any other Casimir operator of any other algebra, this is 0. This is, you can prove, this is based on the fact that these are Casimir operators. They commute with all the generators of the algebra GR, and this property can be proven. I mean, this is an exercise if you wish. But what is essential is that all the Casimir's operators must belong to a particular reduction from the dynamical algebra to the symmetry algebra. That is an essential property. Yes?
I need something between the order of the Casimir operator for SO3.
Yes?
Because for me, angular momentum is act on one body. And you say that the order of the Casimir operators depends on it's one body or two body interaction.
Yes. Okay.
So
Yeah. So because I gave the example here, what was the Casimir operator in this case? The Casimir operator was C2 SO3. Okay, the SO3, it was because it's written in terms of the generators of Lx, Ly, Lz. And the 2 here, the quadratic, it comes from the fact that you have Lx squared, Ly squared plus Lz squared, or Lz squared. Okay, and so you can look as much as you want, but there is no linear Casimir operator in SO3. So because Lx does not commute with Ly or Lz. You can only define a quadratic Casimir operator because that's the only operator that commutes with Lx, Ly, Lz, all of them.
Okay, so the order of M
Yes.
Casimir operator is not necessarily due to the interaction between
No, this will be given by the Lie algebraic structure. But what I meant is that once you have an order here, it will impact on the order of the interaction that you have here. It's clear if you have a linear Casimir operator, it exists, right? Then it is linear in U alpha beta, and so it must, in the end, reduce to a term of this kind. Yes.
What are the Casimir operators about U omega?
There are none, actually. There is a little, I mean, this is a technical thing. Well, no, I should say, well, let me not get into technical, because this is, technically speaking, it's not a Lie algebra, it's not a classical Lie algebra. You should also only look at SU omega, but forget about that. But the linear operator here is very simple, right? It is alpha, U alpha, alpha. It's the sum, it's the number operator, right? This, remember, so this will be C alpha, alpha. Okay, and I think this was the next, this you showed, right, somewhere, right, to show that here you count the number of particles, okay? And so it's rather easy to show that the number operator commutes with all the generators. So the linear there is the linear Casimir operator of U omega is just a number operator, okay? Yes, that's it. But to define the labels, as I said, I made this comment that the number of Casimir, independent Casimir operators defines the labels associated with an algebra. This is only true for the classical algebras, and this is, strictly speaking, not a classical algebra. So, okay. So this means you have now expressed your Hamiltonian in terms of a set of commuting operators, and then from basic quantum mechanics you know that you can solve this Hamiltonian, and so we will see many examples of that. And so let me,
I have a question.
yes.
Why we are taking Casimir operators until quadratic order?
Yes, this is maybe, I should give no upper limit. There is no fundamental. I just put here a 2, that if you want to go only up to two-body interactions, then you stop at 2. Okay? But there is no fundamental reason. So this technique can be applied to higher order interactions as well. Yeah, let me summarize. So this is, I have here, this I would call algebras that break the original dynamical algebra, and then in the end you have something which is associated with the symmetry of the Hamiltonian. And I think you see you have here a to answer your question whether this is only the Casimir operator of, so in this example if the symmetry algebra is SO3, right, it's clear that you have more Casimir operators than just the quadratic one of SO3, right? So you can write your Hamiltonian. It has a much richer structure than just L squared, right? But still, if it commutes with Lx, Ly, Lz, then SO3 is a symmetry algebra. So here, typically, so this will be U omega, and so the associated quantum number is just, as I showed here, it's associated with the number operator, so this will be the number of particles. Let me use, right. Here, this I've already mentioned several times, so let's suppose that this is SO3, then the associated quantum number is the angular momentum, right? And the symmetry implies that all the states ML, right, all the magnetic substates are degenerate, right? And here you have, in general, that is the nice thing about this dynamical symmetry. So you have a quantum number associated to each algebra that is intermediate, right? Let's call it, I don't know, sigma. Right. So you can now define a number of labels in addition to angular momentum, in addition to particle number, a number of labels, and these labels, they allow you to classify your states, to find selection rules and things like that. This is not the only example of a symmetry algebra. So this I would say SO3. Another example of a symmetry algebra, this we will discuss, is SU2 associated with isospin, the isospin algebra SU2. So this is one example I will discuss now immediately in detail. I think that's about it. There is one additional feature which is nice. So this is dynamical symmetry. And so what the features are, all the eigenstates are solvable. So you have a simple energy expression for the energy of all the eigenstates, the entire spectrum. So even if you would have 1,000 particles here, you can get an analytic formula for the energies of the eigenstates. So maybe I should, all eigenenergies are known analytically, let's put it that way. So you will have, let me remind what was. And eigenstates are solvable. and this is perhaps the most important property, the wave functions have a fixed structure. What do I mean by that? So you have a number of parameters or coefficients in this Hamiltonian, right? Now, in a general case, if you have a Hamiltonian like this, with single particle energies, two-body interactions, and you change the values of those coefficients, then the structure of your eigenstates changes. Okay, that is general feature. Here it is different. So you change the coefficients here, nothing happens to the structure of the wave functions. The wave functions will remain with the same fixed structure. We will see several examples of this in the exercise sessions, how this works out. So this is a very important property, because this immediately leads, since the wave functions have a fixed structure, they do not depend on the coefficients in the Hamiltonian. This immediately leads to selection rules, okay? Because you work out transitions between levels once and for all, since those wave functions do not depend on the parameters in the Hamiltonian, they are valid for any case. Yes?
What is the physical meaning of the selection rules from the dynamical symmetry? Or what we can say about that?
The physical meaning, I mean, see, what you will try to do for selection rules, I mean, this is getting ahead a little. I mean, I will discuss some example which is related to E1 transitions, but you need to construct observables. I mean, for instance, you have a transition, okay? Associated with this is an operator. I assume that this operator can now be written in terms of the generators of the algebra, okay? If that is the case, right, then this is correctly called the dynamical algebra of the problem, so you can describe it within that algebraic structure. Then you will now introduce this operator and try to calculate the matrix elements between wave functions that have a fixed structure, okay? And this can be done independently or whatever parameters you have here. I will show an example for E1 transitions in nuclei and isospin symmetry, if I have the time.
So,
Yeah.
I just want to ask, are we going to do this in practice? Like, we just have some system.
Oh yes.
So, I mean, the general idea is, okay, I have some system, and when I have some system, I can just think about, okay, it has this and these symmetries. Then I should get a dynamical group that goes into this chain and ends up at this symmetry.
Yes.
And hopefully, when I get the Hamiltonian with some coefficients.
I think we will do nothing else than that actually for the remaining well, a lot will be like that. I mean, so at least the lectures of Jan Joly, Rick probably also will discuss the IBM. This is precisely this kind of idea one will follow. I will give a lecture on shell model, and so I will also follow this idea of defining symmetry algebras, dynamical algebras, looking at breakings, defining the quantum numbers associated with it, etc. So let me just, because this is well known from the interacting boson model, right? Where this is U6 and this is SO3, and most people will have seen something about that. But this also happens in the shell model. So in the shell model you can discuss things in a similar way. So let me just, maybe I have one, and I don't have to write it. Yes. Right. So I will discuss in a moment isospin symmetry. There is also there is a relation with seniority, and I will discuss my lecture seniority in terms of, well, this is SU2, but you can also show it's associated with the symplectic algebra, so I will go through that in detail. There is the interacting boson model, as I said. So there the dynamical group is U6, the symmetry group is SO3, and the various breakings are here. And these are the physical features associated with these breakings. This we sort of already saw in the lectures of Rick. And there is also, this I will also discuss, super multiplot. This is a very old model by Wigner. And especially important is SU3, because that is an explicit model where you show that within the spherical shell model you can get rotational features. So this you also will, and probably Mark Caprio. I should say that one of the lecturers has arrived, which is Mark Caprio, which is sitting in the back. And so he will discuss rotational features in a shell model context. So that will make contact with the idea of SU3. Okay, yes? It's essentially a mathematical problem originally. So when one can use this, right, so if I understand the question well, let's do this for U6, right? We know we have S and D bosons, so the dynamical algebra is U6. We want to construct Hamiltonians with a rotational invariance. Okay, so you have to get from U6 to SO3. And this is a mathematical problem, the different ways how you can get from U6 to SO3. It's not so difficult, but it's essentially mathematical. And I should say that there is a connection, for instance, between SU3 in the boson model and SU3 in the shell model. So this has been applied, for instance, in the SD shell, okay, and this applies to S and D bosons. So you see that there is some relation between the two SU3s. They're not identical, but they are at least related. Okay. Let me discuss an example to isospin symmetry. I will spend some time on isospin because this, I think, is a difficult concept. So here it is written. So this was something which was suggested a long time ago. Heisenberg in 1932, Wigner in 1937. And so what are the empirical observations? I mean, you have about equal masses of the neutron and the proton. They both have spin 1/2. And neutron, neutron, proton, proton, neutron, proton, strong forces are similar. They're not identical, but they are similar. And so these two features led Heisenberg to propose this idea of isospin symmetry. But the equality of the interactions is also an important feature, and that was stressed actually by Wigner in this later paper. Okay, so the idea is we define two charge state of a nucleon. 1, 0, so this would correspond to a neutron, and 0, 1, this corresponds to a proton. Okay, and so the idea is now, if there is isospin symmetry, then you can rotate in this isospin space and or transform, do unitary transformations in this isospin space, and the Hamiltonian should be invariant under those transformations. So that would be the definition of a Hamiltonian which has isospin symmetry. It is invariant under those transformations. It commutes with the transformations between the different isospin states. Now, how do you write in general such a transformation? And this is one way of writing it. Right, I will try to follow the notation. There is in my notes there is a sort of a more lengthy derivation of this equation, but this is a standard derivation, so I will put the notes on the website just after the lecture. So 0. Okay, so these are the Pauli matrices. Okay, so these were the matrices introduced to discuss the spin of fermions, of spin 1/2 fermions. And so you see the derivation which is given in the note shows that the isospin transformations are completely identical, at least mathematically, with the Pauli matrices. Okay, and so you have 3 matrices. Let's call this Tx, Ty, and Tz. Okay, and then you can define combinations T plus minus Tx, T plus minus Ty, and then you can show on the basis of these commutation relations that Tz, T plus minus T plus minus T plus minus, and T plus T minus is 2Tz, if I'm not mistaken. Yes. Okay, and so now the action, this you can show with the explicit matrix representation and with these basis vectors. It's quite logical. For instance, if you the convention is that the neutron has isospin up and the proton has isospin down. So if you want to increase the isospin on a neutron, for instance, a neutron state, then this gives 0. I don't know, T minus on a neutron gives the proton Tz. On a neutron gives plus, right, and Tz on a proton gives minus P, and so on. Okay, so this is easily derived by using the matrices here in this representation. Okay, this, yeah. Oh, this is just a conventional factor. I mean, I could, but these are the parameter. The idea is, you see, the idea is you have transformations, unitary transformations between these states, okay? This is an infinite set of possible transformation because they depend on continuous variables. You have continuous transformations, right? And that would be actually, those transformations would form a group, a Lie group, right? They depend on continuous parameters. Here it is much simpler because you see now I can write any transformation in terms of infinitesimal transformations. These are small numbers, right? Right. So I have an infinitesimal transformation t times tx, an infinitesimal transformation times ty, and an infinitesimal transformation times tz. And this is the most general infinitesimal transformation I could do. In fact, from those tx, ty, tz, and then suitable parameters, I can generate all possible transformations, right? So this is the idea of a group versus an algebra. A group would be all transformations, whereas an algebra, it's confined to infinitesimal transformation. But you see here, it is infinitesimally different from just the identity, right? So you have the identity plus a small transformation. There was another question which disappeared. Yes.
I was going to ask the same thing.
Okay. So this, I guess, for one nucleon, this is known. Right. So what you have to do now is to, and then it becomes more difficult, to apply this to A nucleons. And so now I use capital. I will not write x, y, z or tz, t plus, t minus repeatedly. I just will give it an index, mu. Right? So mu can be -1, 0, +1. Okay. And what is for an A particle system my isospin operator? Is you have a summation for over all the particles, and then you have the isospin associated with particle k, where the t mu's are defined in terms of those. Okay. So now we can formulate the question of isospin symmetry. So what does it mean? Following the terminology I introduced just a minute ago, right? We have a Hamiltonian that commutes with the generator, the isospin generator. So remember, this is a Hamiltonian which depends on the k particles. So now we can assume, and this was assumed by Heisenberg-Wigner, that the nuclear Hamiltonian commutes with the isospin operators. Yeah. Yes, well, or combinations of them. So these combinations, yeah, I think there is maybe, I could have a factor square root of 2 here. Sorry, they say 1 over square root of 2.
So by T0 you mean TZ?
Yes, yes.
Okay.
This you shouldn't take, I should have checked that, but I think it's 1 over square root of 2. Yeah. Okay, so what is the property of a Hamiltonian that has isospin symmetry? So now we can apply our rule, because these are identical commutation relations as for SO3, or for some reason this is called SU2. I don't want to get into that, but the algebras of SU2 and SO3 are the same. The point is that for SO3 I had integer, so I was talking about orbital angular momentum, so integer valued. Here I have spin 1/2 object, so the representation can be half integer, and then one has to use the terminology SU2. Right. And I will talk here about SU2, and I put an index T to remind myself that this is the SU2 algebra which is associated with isospin. Okay, because, this I should have said, but these capital T's, so the many body, I mean the ones that act on all the particles, they have exactly the same commutation rules as the individual T's. Okay, so let's suppose we have a Hamiltonian with this property. This will be approximate, we know that, because the Hamiltonian, of course, is also, the nucleus has also protons, and you have a Coulomb interaction between the protons, but not between the neutrons, so certainly there must be some difference in the interaction between the two, so but let's forget about that for the moment. Then I have eigenstates, right, which will be characterized by a set of quantum numbers that I don't know. This could be the spin, the angular momentum and its projection, but certainly I will have a quantum number isospin and its projection mt, right? And all the states with mt for minus t to plus t, they are degenerate. Right? So this is the property of degeneracy that I mentioned associated with the symmetry. Okay, and so I have, of course, t squared acting on this is tt plus 1. And tz is mt now. This is easy to understand what it is. Tz, so it's just a sum over these operators. This tz operator has the property that it gives 1/2 for a neutron and minus 1/2 for a proton. Yes?
So this isosymmetry, I guess I'm a little confused, because the binding energy of 100 neutron ball is different than the binding energy of 100 proton ball.
Yes. Yes. So I will come to that. So this is, you would think this must be a terrible approximation, right? I mean, this cannot be true because there is this huge binding energy difference. It turns out that actually the quantum number is reasonably well conserved, even notwithstanding these huge differences in binding energies. These are mainly diagonal shifts between the two without affecting the wave functions. And so you make contact with this idea of dynamical symmetry, where you split states, but without changing their structure. Yes. Well, okay. Yeah.
Just a question. So there is no h bar square or h bar vector.
No. It's formally equivalent with angular momentum, but
Yes, apart from the difference between the proton and neutron energies, there is also a point that neutron is not stable and proton yes.
Yes.
How it can be put in this framework where you have annihilation and operators which can create or not a proton or neutron from a proton or a neutron, I don't know. Can we plot something which break this symmetry?
related to the decay properties of the particles. That's your question, right? I don't know, but basically the decay property comes from the mass difference. Huh? So it's just that, I mean, one is higher than the other, so the neutron decays.
Yes, but my point is,
And that can be put in rather easily.
but in this description, it seems that neutron can become a proton and vice versa in the same way,
Yes.
but it's not the case. It's just consider neutron and proton in the vacuum. So
Yeah, I'm not sure. I mean, a beta decay operator so would transform well, beta plus, beta minus, a neutron into a proton into a neutron. So certainly you can describe beta decay with these operators. Well, Fermi beta decay. So you just change the neutron into a proton or vice versa without changing the spin. And that can be modeled by these operators. Right, but it's in a many-body context, so I don't know about one. I mean, the decay of the neutron. You can also have gamma of Teller decay, and then you change a proton into a neutron or vice versa, and you change the spin. This requires some modification, but you can also discuss it algebraically. Where was I? Yes, I was saying here, so you get plus 1/2 for a neutron, minus 1/2 for a proton. So you act, right, on A nucleons, n of them are neutrons, z of them are protons, so you get something n minus z over 2 TMT. Okay, and so Tz is actually always, or MT is always a good quantum number, right? It's just the difference between neutrons and protons. And there is some, how do you say this in English? Abus de langage.
What?
Abus de langage. Abuse of language. Let me give a. People often talk about n minus z and they immediately associate it with isospin. It is, strictly speaking, I mean, it's fine. I mean, if you know what you're talking about, it's okay. But strictly speaking, it's only the z component of the isospin which is meant. Okay. This empty is always conserved.
I mean the particle number. You said particle number.
Oh, yeah, but that is a defect of the theory. So I know. I mean, there are of course ways to solve where you do not conserve particle number, and then you have a problem with MT. I agree, but that's a problem of the theory. I mean, the reality has, well, as far as we know at the moment, there is charge conservation, so this will be a conserved quantum number. Yes, but you're right. I mean, yes, if you discuss isospin symmetry and Tz symmetry in the context of a model, you might have a model where this is not conserved. Yes, that's true. Okay. What do I do now? Okay, so as it was remarked already, we have a Coulomb interaction between the protons, and this will strongly violate this degeneracy. So can we now make an estimate of how to treat this in this context? So there is, I should say, there is also, of course, an isospin violating component of the nuclear interaction. But let me give the argument with Coulomb, because we all know. Coulomb, so the interaction, yes. I can have TZ. And maybe there is a factor. Oh, that's it. Okay, we know, so you must have the TZs done for the two particles in order to have the interaction, okay? And so now you can do something, you can do a decomposition, a tensor decomposition in isospin. This I will try to explain, because that's, so there is one trivial thing, of course, is that you just write this out, 1/4, and then there is okay, well, and then I'm really concerned about this expression and what does it mean? Okay, this is a constant, so it's a scalar. This is a vector, so it's the z component of the isospin vector. Okay, so but what is this? And it turns out that you can write this. I will try to follow my notation here. Lambda is 0, 1, or 2. Lambda Coulomb. Yes, I would. This is the notation I used everywhere, so we stick to it. Okay. The important point, and this is a difficult point, people struggle with this. Isospin, so the Coulomb interaction has a scale, an isoscalar, an isovector, and an isotensor component. And so why does, because this is confusing, people sort of say, but my nucleon has spin 1/2. So if I put two nucleons together, how do I get the tensor, right? How do I get lambda equals to 2? Right? How does that come about? But you should remember, this is a vector. So this is an isospin vector. So it has three components. It has z, and then x, y, or plus minus. Right? And so the vector, you can couple, of course, to 0, you can couple to 1, and you can couple to 2. So there are the three components of the isospin of the Coulomb interaction. So it can be scalar, vector, and tensor. If you would like to think of this in second quantization, this is another argument, right? So if I forget about all the labels, but I just label my particle with the isospin quantum number, okay, then indeed I have a creation operator with, yes?
Can you explain again why TZK is a vector?
Because it has three components.
For me, it's the Z component
No, what I mean, it is the third component of a vector. Okay?
That one is a scalar name. The component of a vector is a scalar name.
No, but if you do a transformation in this space, you will get to the other components. Okay, so let me repeat the argument, but in a different way. So you have particles, creation operator, so you have isospin 1/2. They have two indeed. This is an isospin 1/2 object, okay? But now to create the isospin vector, so what I called T associated with a certain particle, this you construct in this way: 1/2 coupled with, well, the annihilation operator. I put a tilde, but that will become clear. And this is coupled to 1. Okay, it has 3 components. I usually don't vector it. Right. Okay, so here you see you take a creation operator and an annihilation operator, and this is a vector. And now you see that if you take 2 vectors together, so you have an isospin 1 object, you can couple to scalar, vector, and tensor. So the 3 possibilities are there. Now it's a technical matter to rewrite this. This is a scalar, right? That's obvious. This is a vector. I mean, this is a component of a vector. That's also obvious. This is a bit more difficult. How to get this, right? I can give you the result, and then you can struggle a little trying to derive it. Right, so I hope I convinced you that you have the 3 components available, and so now, I should perhaps indicate here what is the projection in isospin. And the projection is always 0. Right, this is what you said. It's the z component of a vector. So the projection, you don't change. The projection is associated with particle number. This interaction doesn't change anything about particle number, so the component here is 0. Okay, and so let me now write the expressions. This will maybe baffle you a little bit, but it can be shown. This is basically getting this from Clebsch-Gordon coefficients. Right, so you couple this to angular momentum 0, and you take the 0 component. And then you have here always the same factor which does not interest me. Okay, so this is the scalar part. The vector part, this is trivial because it's immediately here. So it's the z component. Okay, times the same factor. And then you have the coupled to 2. So yeah, this is z0 times the same factor. And so this is isoscalar. Excuse me?
There is no vector part coming from the tensor component of the Coulomb interaction.
This I don't understand as a semantic question. I have a problem with that.
Okay, have a look at the isovector part now.
Yes?
Yeah, and you got the component, you added these 2 vectors, yes?
Yeah?
And is there no
this is here. Oh, I see. No, no.
This is 0.
This is 0. Yes.
And why?
Well, it comes from Clebsch-Gordon coefficients. I mean,
Okay.
yeah. This would take me some. Okay, I can. But it's basically what you want to do is to. Yes, it's a good question. Yes, yes. So I just didn't understand it. Right. So you want to do this kind of problem, right, where you couple it to lambda, and if you use you look at the zero component because there are 0 components, and you write it out for the different lambdas, right, and then you try to fix with Clebsch-Gordon coefficients, right, and then from these combinations you can derive these results. But you're right, yes, it's not obvious. Yes. Okay. What time is it?
6.
Okay. Yes, I probably only will do this example because I would like to discuss one more thing which is very useful, and this is the Wigner-Eckert theorem, and you have a beautiful application of the Wigner-Eckert theorem from this. So this is our Coulomb interaction. We have written in as components isoscalar, isovector, and isotensor. Okay, and so now we're going to use this in a basis which defines in this way. So the idea is we have a Hamiltonian which conserves symmetry, isospin symmetry. To this Hamiltonian we add the Coulomb interaction. Okay, this we consider as a perturbation, right? And so now we will calculate matrix elements in first order perturbation theory. Okay. So I had states which were so move. Okay, I had my V lambda here, the 0 component. I'm not going to write the summation of all the particle indices, and I want to calculate this kind of matrix element. Okay? And so now I can do something rather neat. I can say this is characterized by spin isospin projection. This I have decomposed, right? So I have looked at the character of the interaction and decomposed it according to its transformation properties in isospin space. So, and I found out it's either scalar, vector, or tensor. And here again I have TMT. Okay, and then this is multiplied. This was already mentioned by Rick, by a reduced matrix element. Right. Okay, this is a reduced matrix element. And the reason that you can do this is due to the Wigner-Eckert theorem. Okay, let me first say something about the general structure you see here you have a matrix element that depends on T and empty. Okay. The empty dependence is now completely removed from this reduced matrix element. Okay, so the empty dependence is completely contained in the Clebsch-Gordon coefficient, and which is multiplied by a reduced matrix element. So what it means is you have to calculate this matrix element for a choice, one choice, particular choice of MT, right? Whatever is most convenient, and all the others follow from it. And the other thing I should mention that there are some different conventions for this reduced matrix element. Some people will put here instead of a Clebsch-Gordon coefficient a 3J symbol, so then you have some factor which comes in 2t plus 1 or whatever. So, but the basic structure or the basic idea doesn't change. This is very important. So this is an illustration of it in the context of isospin. It's probably more familiar to all of you in the context of angular momentum. So let me just write the equivalent thing for angular momentum. So for angular momentum, I have the same kind of, for instance, you have a transition. Let's talk about something where you have an initial state characterized by angular momentum Ji, which does a transition, maybe electromagnetic transition, whatever, to a state which is characterized by final angular momentum Jf. Okay, so you need for this kind of process to calculate a matrix element of this type, right? So here you have your transition operators. Let me follow. Yes, I've done the same. Lambda, projection mu. Here it is Ji Mi. It's conventional to put here the initial state. The operator acts on the initial state to give the final state, and so the Wigner-Eckert theorem tells you that this will be equal to lambda mu Jf Mf times the reduced matrix elements. Okay. And so what you should realize, just some side comment, that this is a general mechanism. Okay, so in this example, this was something which is associated with SO3 here is the ensemble of Jx, Jy, Jz, and SO2 is just the Jz operator, right? And so the associated label, I should put this different. This is right, so it goes, the reduction is SO2, which is just one single generator. The associated label here is what I call J, and here it will be the projection M. Okay, and so you see this has associated with it a Wigner-Eckert theorem where you factor out the dependence on this guy. And actually this is a general mechanism in terms of two algebras. Right. So I would like to follow the notation. So here gamma. This is a side remark, but I think this just to tell you that this is a very powerful theorem which can be generalized to many algebraic structures, right? And so now, as we will see during the coming days, if you have something which corresponds to a chain of algebras, you have labels associated with them, so you can likewise consider situations where you have an initial state characterized by these labels, then a transition operator, which, how did I label it? Yes, gamma, why not? Right. And then the final state here, right. This can always be written as some kind of a generalized Clebsch-Gordon coefficient. Times reduced matrix element. I'm not going to use this, but I just would like to mention that this exists. And so the same kind of mechanism. So here we have reduced matrix elements. Here it depends only on the properties of the large algebra. We have here generalized Clebsch-Gordon coefficients. Suppose we can calculate those generalized Clebsch-Gordon coefficients. Then we can calculate, and we only have to calculate one matrix element here, and we have all of them. So this is a general applicable theorem, so this Wigner-Eckert theorem. So what I did there is to apply it to the case of, again, this was SU2 to SO2, right? So this is SU2 associated with isospin and SO2 associated with the projection of isospin.
Write down the definition of this generalized reduced matrix element.
It follows from this relation.
Right, so I imagine, is it just the same as the angular momentum reduced matrix element, but replacing the labels with general labels?
No, I'm not. The question is about.
Well, right now we've just written this reduced matrix element, but how is it defined? Like when you unpack it?
Oh, it's defined through this equation. Huh? So there must be a way to calculate at least one of those matrix elements, and if you can do that, and if you know the Clebsch-Gordon coefficient, well, in this case it's just an ordinary Clebsch-Gordon coefficient, we know it, then you can deduce the reduced matrix element. Okay? Is that clear or?
Yeah, it's still not quite what I'm asking. Like normally we can just write out the reduced matrix element, like the definition of it, right? Or no?
Maybe you
You
can.
Matrix elements with this m projection quantum numbers. Like you calculate just once for one quantum number, then you can have whole matrix elements just because of this formula. Yeah.
Okay, maybe. Okay, I have 10 more minutes, so I would like to get to the. Yeah.
Because in the example in the bottom line, you have gamma in parentheses, big gamma, and which is, yes, you have the two gamma on the operator T.
Yeah.
But when you look at on G, there we have lambda mu, which refers also to G and N, or?
So the lambda here, this would refer to SO3. And the mu here, this is the projection, it refers to SO2. Yeah. And I stress this is only a side remark, so you will be maybe baffled by this kind of, and even you can do it, this can be a chain of algebras, and then you can decompose these generalized Clebsch-Gordon coefficients. But, well, never mind. Okay, so let me erase this. okay, so now I come back to here. Okay, so this can be a scalar. So this is 1 that I know by heart. 0. This Wick should know. Because it must be empty, that I know. Empty. It's linear in empty. And then the vector, the tensor, sorry. The tensor is quadratic in empty.
That's the one I made.
Excuse me?
That's the one I made.
Ah, okay. Okay. So now we have derived this matrix element in first order perturbation theory, and so in first order perturbation theory you would have states with energies due to the Coulomb, right, which can be written as a constant 0 plus something which is mt plus something which is mt squared. Okay. Where these coefficients, they depend on n, eta, any of the quantum numbers, and also on isospin. And so this, I guess, you must have seen already somewhere. So this is known as the isobaric mass multiplet equation. Which was proposed by Wigner in 58 or something. Okay. And so in this is so you get this equation just by looking at the isospin decomposition of the Coulomb interaction and then applying the Wigner-Eckert theory. This is first order perturbation theory. This does not mean that Coulomb interaction will not break isospin symmetry, because of course if you look at this matrix element, right, eta t mt, and now I take v lambda 0 eta prime, well, t. I convinced you that the mt on the left and on the right, that will be conserved, but this in general, right, is different from 0 if t prime is different from t. And this for the well, if it's a scalar, of course it cannot change t from t prime, okay? So the scalar contribution of the Coulomb interaction, which is the bulk actually, this is the most important, it will not change the isospin. So that will be isospin conserving. However, the isovector and the isotensor, they might change isospin. So this is in general different from 0 for lambda equals 1 or lambda equals 2. Yes?
Can I ask a question about, so if I take some isobars and start plotting their masses relative to each other, would they follow this formula?
Yes, to a large approximation. I have
Do
some.
you have a slide with this?
Yes, I can show. That will be actually the last thing I have to show. Right? Yes, I'm doing. So these are examples of isobaric multiplets. So this is, right, so the mass of the two, I hope this is visible, but the mass of the two is 49, okay? So this is chromium, 24 protons, 25 neutrons. Here it's the inverse, so these are mirror nuclei. If you just do the counting, or in terms of isospin projection, so this is MT plus 1, MT minus 1/2, and look at the spectra. So this is the experimental spectrum for the two nuclei, and what you say is true. So there is a big shift between the two, right? And that would be even increase if you make the difference in.
Should we do this with like bigger isobaric?
Yes, yeah, I will
so
show.
We will see some like some parabola or not parabola.
Yeah, I will show in a moment. But I would like to discuss a simple case. Okay. So you see that the spectra are very similar, although they are displaced in energy. Okay. This inset here shows the differences in excitation energy as a function of spin, and you see these differences are not larger than 100 keV. Okay. So that means that energy in both spectra are similar. But let me come to an example of a multiplet, an isobaric multiplet. This is another example of a doublet. This is a multiplet. Right. So this is A equals 32, right? And so this is a quintuplet, right? So this is T equals 2, okay? T equals 2, right? So MT, or N minus Z over 2, goes from minus 2 to plus 2. So you have 5 nuclei in the quintuplet, and they are here. Argon up to silicon. So argon is what is the 18, right?
18.
Yes, 18. So MT is, well, minus 2. Yes, minus 2. Okay, because you have more protons than neutrons. And then, of course, necessarily, T must be 2 or higher, right? But the ground state will be the lowest possible T, which is compatible with MT. Okay, so this is one extreme. The other extreme is silicon, so it is MT plus 2, T2, but then you see also it associates states. These are excited states in chlorine, sulfur and phosphor. Okay, that's important. So the ground state of sulfur here, sulfur is 16, right? So it's 16, it's an N equals Z nucleus. So the MT is 0. So the T in the ground state, most likely, well, but I think it will be 0. Okay, for N equals Z nucleus, no, it's even, so it's 0. But then you have also in the spectra T equals 1 and T equals 2 states. Okay, so this is an excited state in sulfur. But it belongs to the same isobaric multiplet. So if I would apply T plus, so sorry?
Shouldn't be, I just mean for the ground state, shouldn't be 1, like in order to have angular momentum 0 for the ground state.
But I'm discussing the T equals 2 states. I agree with you.
I understand. Like I mean, to have in order to have the ground state of this nucleus zero,
Yeah.
the angular momentum zero, then you should have isospin one.
Oh, but this is for you have protons and neutrons. Huh? So, yes, I understand your question. So if you have two identical particles coupled to zero, then of course you have T equals 1. But here, well, already it's difficult to talk here about two particles, but they would be a neutron and a proton. But I think no, you cannot look at this as a, what would it be? So one nucleus plus a neutron and a proton. No, this is. You're right. If you look at n equals z nuclei which are odd, then you don't know in advance whether the ground state is T equals 1 or T equals 0. That is, but these are the only nuclei where there is some question about it. For all other nuclei, the ground state isospin is always empty. Always. Sorry. That's an empirical fact. But so the ground state of this nucleus will be a 0 plus. Okay. So you're looking at excited 0 plus states in sulfur here. The energies will be tens of MeV, I think, right? Because this is T equals 2, right? But the structure of that state is very similar to the structure of the ground state of argon, or the structure of the ground state of silicon, right? And you go from these states are connected by these T plus operators, right? So if you act with T plus on argon, you should get to this excited state in chlorine, then you get to the doubly excited state in sulfur, and so on. Okay. This isospin is not so easy. And so this is an example of a quartet, so with half integer isospins, because it's non-mass.
Is these examples a little bit filter out, or you should take it for any set of isospins you get that?
Yeah, this works rather well. Let me show.
So isospin is very good symmetry.
I don't know whether that is a conclusion you can draw from this, right? You can only say, well, this is sort of a formula that works, right? But this is not really a test of to what extent that this is a good quantum number. Let me show you one more, and then I stop, because it's 33 already. This is, you see, this is C3. C3 would be in this notation here, kappa 3. So you see, you can fit now all the isobaric multiplets that are known and see whether there is a third, here a cubic dependence on MT or not. And you see that most of the multiplets that are here, so you see for each point, this is a set of nuclei, like this. Each point is a set of nuclei where you have fitted such a formula. Okay, and you see that most of the nuclei are consistent with a coefficient C3 or kappa 3, which is 0. Okay, I think I will stop here. If there are urgent questions, you can ask them now. Otherwise, we have the afternoon. But
Which is the common way to determine which symmetries are involved in the nuclei?
the common way. Could you be maybe more precise? Because
Because sometimes, okay, I know that we try to identify identify the degrees of freedom of the system, and we can associate sometimes symmetry, but not always works, because sometimes the symmetry is not is always strict, and when we want to determine energy for another quantities, doesn't work the model. So what we can infer about that?
Well, I don't know whether I can answer this satisfactorily, but I would say the choice of your dynamical algebra, that has to do with the degrees of freedom, right? That you want to include. That, of course, this is a physics choice. Huh? Like IBM, you say, well, I have an S pair and a D pair, and that is the most important degree of freedom for my model, and I will include that. But you might do octupole or whatever. Okay? So that defines your dynamical algebra. Rick has a better answer.
No, better. How do you know it's better? No, I have a...
Help me.
Maybe I understood the question a little differently.
Oh, okay.
Suppose you talk about dynamical symmetries. Okay, you have this chain of groups. Each group in the chain defines a certain quantum number, which is associated with the levels, and there's an energy expression, an eigenvalue expression, for how the energy should go as a function of that quantum number. And so you have a nucleus, you look at the energy levels, the spins, parities, and so on, and you ask, does it look like one of these symmetries? Does it satisfy those equations? Okay. And in general, it won't, because these group theoretical descriptions tell you what a nucleus can do, but not whether any given nucleus does it. And so if it does it, if you're lucky, then that's great. You can assign that symmetry. If it doesn't, you can look to see if it's close to that symmetry, close to those analytic formulas. And if it's close, you might take the Hamiltonian and add some terms that break the symmetry and then diagonalize it and see if you can do better. Is that an answer?
Okay. So